We're going to look at something called a Taylor polynomial for a function. Here's the formula on how to compute an nth degree Taylor polynomial for a function f near the point x equals a. If you've never seen this before, this formula looks pretty unusual and strange, and until you get a chance to really see how it works out in practice, it wouldn't mean a lot to you yet. So here goes. We're going to look at the example here of the function square root of x, and we're going to find this Taylor polynomial. So because we're doing a third degree Taylor polynomial, we have to plug k equals 0 through 3 into the formula in the upper right corner. You may see it as green. So here you'll see the results when k is 0, k is 1, k is 2, and k is 3. It's worth noting here that in this particular case, a is 9, and that's the point we're computing the Taylor polynomial near. And the function f, in this case, is radical x. Well, in this formula, you'll see what appears to be f raised to a power. It almost looks like we're saying f to the 0, f to the 1, f to the 2, and so on. But the little parenthesis exponents above the f, those aren't actually powers. They're derivative markers. So f0 means the 0th derivative, which is the original function itself. f1 means the first derivative, f2 means the second derivative, and f3 means the third derivative. So in order to finish this third degree Taylor polynomial, I have to compute all the derivatives of f, which in this case is all the derivatives of the square root of x. Here's the 0th derivative, or the function itself. When we plug in 9 to that, we get an answer of 3. And that's what we mean by the 0th derivative at 9. The first derivative is shown here. You'll recall back for basic derivative functions how this works. And since we want the first derivative at 9, we'll plug 9 in there. And the algebra isn't shown here, but that works out to be 1/6. Then we'll take the second derivative, which is the derivative of the derivative, and we'll plug 9 into that. Once again, there's lots of algebra not shown, but this ultimately works out to this fraction. And finally, we'll take the derivative of the second derivative to get the third derivative. And we will once again plug in 9 and do some fancy work on scratch paper, and that will eventually lead to this fraction. Now, if you're not really clear on how negative exponents work or anything, go back to your prior notes and analyze that. I would really hate to turn this into an algebra lecture, so all of the messy details have been omitted for your convenience. Here's the main point you need to know in terms of the calculus. Now that we've computed the 0th first, second, and third derivative, we can plug these into the formulas, and we'll get this. A couple things to note here, in case you forgot. 0 factorial is 1. And now the third degree Taylor polynomial is just the sum of all of these terms. It doesn't look very simplified, so what I've done now is I've done some algebra to simplify this. Here's the final result. And again, to avoid turning this lesson into an algebra lesson, I will not put the particular details, but the stuff that you could use basic high school math to figure out ultimately. This thing at the bottom of the screen is called a third degree Taylor polynomial for radical x near x equals 9. But what does that actually mean? Well, that means that around the values where x is close to 9, this function is very, very close to the square root of x. Why would we want to take the square root of x and write it in such a messy, almost but not quite equivalent function? Well, there's a long history behind that, but it is often nice if we can take a function that's not a polynomial, such as radical x, and approximate it by a polynomial, such as the thing at the bottom of the screen. And there's our third degree Taylor polynomial. Let's find the fourth degree Taylor polynomial for the function e to the x near x equals 0. Here is our Taylor polynomial formula. And what that means, in this case, since we want a fourth degree Taylor polynomial, we have to plug in k equals 0 all the way up through 4. Plugging in 0 through 4 gives us these expressions. Remember, in this particular case, f is the function e to the x. The little parentheses above the f, f0, f1, f2, etc., are derivatives, and the a in parentheses represents 0, or evaluating those derivatives at 0. So in order to finish this Taylor polynomial, I have to compute all the derivatives of the function. Here's the 0th derivative, or the function itself. Here's the first derivative. Plugging in 0 for that gives us a value of 1. Here's the derivative of the function. Remember, the derivative of e to the x is e to the x. Plugging in 0, I get 1. Now, taking the derivative of the derivative gives me the second derivative, which is, once again, e to the x. And you can see that all the derivatives have a value of 1 at x equals 0. Now that I've computed all the derivatives, I can take them and plug them into the formulas. And the sum of these things is my Taylor polynomial, although it's a bit messy and there's a lot that can be simplified here. So after you do a bunch of algebra, not shown here, you will get this polynomial. And what does that mean? It means for values of x close to 0, that this polynomial is very close to the e to the x function. And once again, showing that we can take a function that's not a polynomial and approximate it as one that is. Let's find the fifth degree Taylor polynomial for sine 2x near x equals pi. Here's the formula for a Taylor polynomial. Because I want a fifth degree Taylor polynomial, I have to plug k equals 0, 1, 2, 3, 4, and 5 into this formula. So plugging in the values of k gives us this, and now it's just a matter of taking derivatives and simplifying. Here's the original function, or the 0th derivative, if you will, and it will plug in pi to that, and that gives us a value of 0, you may remember, from the unit circle. Here's the first derivative of the function. You'll notice that the derivative of sine is cosine, and I applied the chain rule here, giving me 2 cosine of 2x. Plugging in pi for x gives us a value of 2. Again, I refer you to the unit circle knowledge you have. Now I'll take the derivative of the derivative, or the second derivative, once again applying the chain rule and remembering that the derivative of cosine is negative sine. Plugging in pi gives me 0. And so on it goes. The derivative of the second derivative is the third derivative. Plug in pi, get an answer. The derivative of that is the fourth derivative. Plug in pi, get an answer again. And finally, taking the derivative of the fourth derivative gives me the fifth derivative. And plugging in pi gives me an answer. The reason for taking all these derivatives is they're necessary to compute the Taylor polynomial. Plugging in all these derivative values and substituting pi for a gives me this expression, and the sum of those is my Taylor polynomial. As usual, we like to simplify as much as possible, so there's a ton of algebra on my scratch paper that you can't see here, but ultimately, this function reduces to this.